Section 5.2, Mean Value Theorem. Mean value theorem. The mean value theorem connects the average rate of change of a function over an interval with the instantaneous rate of change of the function at a point within the interval. Its powerful corollaries lie at the heart of some of the most important applications of calculus. The theorem says that somewhere between points A and B on the differentiable curve, there is at least one tangent line parallel to the chord AB. Theorem 3 says, mean value theorem for derivatives. If y equals f of x is continuous at every point of the closed interval and differentiable at every point of its interior, then there is at least one point C in AB at which the instantaneous velocity is equal to the average velocity. So instantaneous is equal to the average. Let's say that you start in Elkhorn and you drive to Gretna, and your average velocity was, let's say, 40 miles per hour. You are guaranteed that at one time, at least one instant in your trip, you went exactly 40 miles per hour. So somewhere along this path, if the average was 40 miles per hour, the instantaneous velocity was 40 miles per hour somewhere. Exploring the mean value theorem. Show that the function x squared satisfies the hypothesis of the mean value theorem on the interval 0 to 2, then find a solution C to the equation on this interval. The first part of the hypothesis is f of x is continuous on the closed from 0 to 2. Can we say that? Well, if we look at a graph of x squared, there's no denominators and there's no radicals. So this function from 0 to 2 is continuous. Can we say that f of x is differentiable on the closed interval 0 to 2? Well, certainly. There's no asymptotes, there's no jump discontinuity, there's no infinite discontinuity from 0 to 2. So we can say both of these are true. Now we have to find f prime of c is equal to f of 2 minus f of 0 over 2 minus 0. We have to find out where is the instantaneous velocity equal to the average velocity. So we find the derivative. The derivative of x squared is 2x. We have 2x is equal to, if I plug 2 in, that's 4. So we have 4 minus 0 over 2 minus 0. We have 2x, or 2c in this case, we're trying to find a c, is equal to 2, so c is equal to 1. Now what we found is, let me pick a different color here. Here it is. At 1, the slope of the tangent line right here, that's the instantaneous velocity, is the same as the slope of the secant line. That is average velocity. Exploring the mean value theorem. Explain why each of the following functions fails to satisfy the conditions of the mean value theorem on the interval -1 to 1. So we have to find out, is this function continuous on the closed interval -1 to 1? Let's use a graphing calculator to do this part. Let's enter in the function. We have the square root of x squared and then plus 1. And really, this is the absolute value of x plus 1. It's really the same thing. So we graph it, and we find out that the function is continuous from -1 to 1, but there is a corner here. So continuous on -1 to 1? Sure. Then we need to say that it is differentiable on -1 to 1. And that is a no. There is a corner at x equals 0. On letter B, we have a piecewise function. Let's find out if it's continuous on -1 to 1 by making a little sketch of this. When we plug 1 into the first little equation here, to the first piece, we get 1 plus 3 is 4. 1, 2, 3, 4. So 1, 4, and that's going to be an open dot. If I plug 0 in, I get 3. If I plug -1 in, I get 2. If I plug -2 in, we get -5, so it's way down here. So to the left of 1, this is what the graph looks like. At 1, we plug 1 in and we get 2. So here's a solid dot, and then this is a parabola, so it continues up like that. Well, this function is not continuous. We can say, is this continuous on the closed interval, -1 to 1? And we'd have to say no here. We have a jump discontinuity at x equals 1. We were close. It happened on an endpoint, but you have to be continuous on the closed interval. You can't be discontinuous on the endpoint. Increasing and decreasing functions. Our first use of the mean value theorem will be its application to increasing and decreasing functions. We have a corollary 1, increasing and decreasing functions. Let f be continuous on a to b, the closed interval, and differentiable on the open. If the derivative is greater than 0, in other words positive each point of ab, then f increases on ab. If we have an increasing function as you go left to right, the slopes or the derivative will be positive at all of these points. If the derivative is less than 0 or negative each point of ab, then f decreases on a to b. So whether you decrease concave up or decrease concave down, the slopes on a decreasing function will be negative. Determine where graphs rise or fall. We have the function y equals x squared. If you take the derivative, that's equal to 2x. The derivative is 0 at x equals 0. So our critical point, the point that we're interested in, is at x equals 0. Now if we make a number line, put 0 here, test -1 and test 1. When we plug -1 in, we get into the derivative, not the original, into the derivative, we get -2. So all of the values of the slopes are negative. So this is a decreasing function from -infinity to 0. Then if we plug 1 into the derivative, we get a +2. So all the slopes are positive. That means from 0 to infinity, this function is increasing. So we have decreasing from -infinity to 0, and we have increasing from 0 to infinity. Now if it said explain or why, we would say f prime is greater than 0. Actually, decreasing is negative. F prime is less than 0, and then on increasing, f prime is greater than 0. And that's a perfectly good reason if they ask for some sort of explanation. Where is the function increasing and where is it decreasing? So let's take the derivative. That's equal to 3x squared minus 4. And we want to know where this function is 0. That's where it's neither increasing nor decreasing. So we add 4, that's equal to 3x squared. We divide by 3. So we have x squared equals 4/3. And then square root both sides. So we have plus or minus 2 over square root of 3. That's where the zeros are. Let's go to the number line now. And we have, let's put 0 in the middle. We have -2 over square root of 3. And we have +2 over square root of 3. Now square root of 3 is less than 2. So when I take 2 divided by, let's say, 1.5, that's probably going to be 1 point something. So I'm pretty safe if I pick maybe -2 and 2 as the test points. So we're looking at zeros of -2 over square root of 3 and +2 over square root of 3. And now I just have to test the points in between. If I plug -2 into the derivative, we get 3 times 4 is 12 minus 4, that's positive. If I plug 0 in, I get a negative. And then if I plug 2 in, I get 12 minus 4, that's a positive also. So this function is increasing from -infinity to -2 over square root of 3, and also from 2 over square root of 3 to infinity. This function is decreasing from -2 over square root of 3 to 2 over square root of 3. If they ask, well, how do you know that? Or explain or justify your answer, you'll say f prime is, on this one, is greater than 0, and f prime for here is less than 0. Other consequences. We know that constant functions have the 0 function as their derivative. We can now use the mean value theorem to show conversely that the only functions with the zero function as derivatives are constant functions. Functions with the derivative equal to 0 must be constant. If a derivative equals 0 at each point of an interval I, then there is a constant c for which f of x equals c for all x and I. All this is saying the derivative of a constant is 0. Functions with the same derivative differ by a constant. If the derivative of f equals the derivative of g at each point of an interval I, then there's a constant c such that f of x equals g of x plus c for all x and I. Applying corollary 3, find the functions f of x whose derivative is sine of x and whose graph passes through the point 0, 2. They're saying the derivative is equal to the sine of x. So what is the function that has a derivative of sine of x and passes through 0, 2? Well, the function that has a derivative that is sine x is negative cosine x, but then it could be plus some constant because the derivative of a constant is 0. Now to find that constant, we plug 2 in for y, and we plug 0 in for x. So we have negative cosine of 0 plus c. 2 equals cosine of 0 is 1. So the constant must be 3. Now to answer the question, we're going to write the function with 3 in for the constant. A constant? We have negative cosine x plus 3. Example 8. Find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following sets of conditions. Letter A. The acceleration is 9.8 meters per second squared and the body falls from rest. We have the acceleration is equal to 9.8. So the velocity is going to be 9.8 t plus some constant. Now it says that the body falls from rest, so that means at time 0 the velocity is 0. So we can plug 0 in for the time and 0 in for the velocity. So the constant is 0. So v of t is 9.8 t. To find the position, we need to find out what do we take times 2 to get 9.8, and that is going to be 4.9. So we have 4.9 t squared plus some constant, but it says it falls from a height of 0, so the position is 0 at time 0. And in this case again, the constant is 0. So s of t, the position, is 4.9 t squared. In letter B, we have the acceleration is 9.8 meters per second squared, and the body is propelled downward with an initial velocity of 1 meters per second. So the acceleration is equal to 9.8. The velocity is, again, 9.8 t plus c, but now at time 0, the velocity is going to be 1. So we plug 0 in for t, so c equals 1. So the velocity function is 9.8 t plus 1. The position function is 4.9 t squared and then plus t. That'll come from the 1, and then plus some constant. Now again, the body is falling from a height of 0, so 0 equals 4.9 times 0 squared plus 0 plus c. That means the constant is all 0, so s of t is 4.9 t squared plus t.